Hello, chemistry class, and today we're going to talk about something called enthalpy. And you may or may not have heard of it before, but enthalpy basically just means the heat of a reaction. And it is designated by a delta H. Sometimes there's a delta H with a little p. That little p just means we're looking at the enthalpy, the change in enthalpy at a constant pressure. And basically, delta H, or change in enthalpy, means the energy that flows as heat. So when we talk about enthalpy of reaction, we are talking about energy as heat of that reaction. A calorimeter is a device that is used to measure that enthalpy, the heat associated with a reaction. That can be really useful once we know the enthalpy of one reaction. We can use that then to look at other reactions, and we'll look at how that might be useful in a little bit. But right here, this calorimeter essentially measures the change in temperature of the water that is surrounding whatever the system is, the material that you put in there. So from that, we can determine how much heat is associated with that reaction or that material. This is just a review about exothermic and endothermic reactions again. Here we have an exothermic reaction. We have a reactants here for energy and products here. So this is exothermic. In an exothermic reaction, the enthalpy, the change in enthalpy, is negative. Over here, we have an endothermic reaction. Our reactants here, our products are at a higher energy. It is endothermic. It is taking energy in rather than giving it off. And in an endothermic reaction, the delta H, the change in enthalpy, is always a positive number. So those are just some important things to keep in mind. We're going to look at what if we have, what if we have a delta H right here, change in enthalpy, and it's 180 kilojoules for the reaction. So this is a positive number, it's not a negative number. Let's say we're looking at this system, some reaction, and we have a positive enthalpy change. We have 180 kilojoules for the reaction. We know it's endothermic, right? Let's say this is the reaction. Nitrogen gas and oxygen gas producing two nitrogen monoxide gas molecules. What would the enthalpy, change in enthalpy, be for this reaction? And I want you to notice that here we have nitrogen and oxygen, and oops, I made a little typo there. It should be a subscript 2. Here's nitrogen again and oxygen. Those are the same, right? Here's our nitrogen monoxide and our nitrogen monoxide. Do you see that this reaction is just flipped? I basically reversed it. What would the enthalpy change be for this reaction? If I have 180 kilojoules for that forward reaction, I am going to have negative 180 kilojoules for the reverse. So the nice thing about the enthalpy of a reaction, when we reverse that reaction, it is simply the opposite sign of what the forward reaction was. So I know that when I go this direction, I am going to take in 180 kilojoules of heat. When I reverse that reaction and I go the other direction, I'm going to release 180 kilojoules of heat. Here are a few more things about enthalpy. Enthalpy is a state function. It is a change in energy flow as heat, a particular type of energy. And that change in enthalpy is completely independent of the pathway for the process. So that makes it a state function. Doesn't matter how you get there, the path of the molecules, it is a state function. It is not dependent on how you get there. And then here is where we get to another important aspect of enthalpy, and that's Hess's law. This is really simple, so you're going to like this. Hess's law states that the change in enthalpy is the same whether the reaction takes place in one step or multiple steps. So let's look at this example right here. If we have an overall reaction where we have methane and oxygen going to carbon dioxide and water, right here, the overall, the net enthalpy for that reaction is negative 890 kilojoules. We can also carry this reaction out in two distinct steps, where here's the first step with these products, and then the second step eventually gives us our ultimate products for the reaction. And notice that the sum of this enthalpy change for this first step and the enthalpy change for the second step, the sum of those two enthalpies equals the total enthalpy for the reaction. So that is what Hess's law states. So let's look at two important characteristics of enthalpy changes. And we need to know both of these in order to use Hess's law appropriately. One of them we already know. If a reaction is reversed, the sign of the delta H, the enthalpy change, is reversed. The second important characteristic of enthalpy changes is that if we have a balanced chemical equation and that reaction, we multiply all of the coefficients in that reaction by some integer, then we also must multiply the value of change in enthalpy by that same integer. And we'll give you an example here. So let's do this reaction as an example. I have some xenon gas and two fluorine molecules produces xenon tetrafluoride solid. And here's my balanced reaction. Xenon is balanced and the fluorine atoms are balanced. So if I am told that this reaction produces 251 kilojoules of energy, if it's producing that much, remember that would be exothermic. My delta H is going to be a negative 251 kilojoules of energy. If I want to prepare this in the lab, and I want to prepare not just this quantity, but let's say I want to prepare twice as much of this. So I'm going to double the quantity. If I double the quantity of that, I end up with 2 xenon plus 4 fluorine produces 2 xenon tetrafluoride solid, and my delta H is also going to be doubled. So my delta H will be 2 times negative 251 kilojoules of energy, which I don't have room to write, would be a negative 502 kilojoules. So just so you understand, when I multiply the reaction, all the coefficients of that reaction by some integer, I also multiply the change in enthalpy by that same integer. Now let's look at a simple example of how we can use Hess's law. Two forms of carbon would be graphite and diamond. You know, graphite is the soft material used in your pencil, and everybody knows what diamond is. And let's say that we are given the enthalpies for the combustion reactions of graphite and diamond. And these are the change in enthalpy values for each of those reactions. Now let's say, though, we would like to calculate the change in enthalpy for the conversion of graphite to diamond. Well, we start with graphite here. I want to convert that to diamond. How are we going to do this? First, we know the enthalpy change for graphite to carbon dioxide is this. If we reverse this reaction, we can then take a second step and look at the change in enthalpy from carbon dioxide into diamond. In order to do that, we will need to reverse the reaction and reverse the change in enthalpy. So here I wrote that out. I take basically I just rewrote that reaction right there with the enthalpy change written out to the right. And then I reversed this reaction. I said CO2 going to oxygen and diamond. Here's diamond and oxygen, right? Carbon is diamond. And I'm going to have to reverse the sign of that enthalpy change. So my delta H here will be negative of the negative 396 kilojoules. Now, if I add these all together, if I add both of the reactions together, I get on the left side and the right side, CO2 cancel out, and the left side and the right side, O2 cancel out. I am getting carbon as graphite going to carbon as diamond, and I'm adding the two delta H values together. That will give me 2 kilojoules of energy. So we just used Hess's law to determine the total change in enthalpy for both of those reaction steps of one larger reaction. Okay, we're going to try this practice problem together because it's a lot more complicated than the last practice problem. We're going to use that second characteristic of enthalpy changes, about the magnitude, when we are looking at multiplying the equation by a coefficient. We also need to multiply the change in enthalpy by that coefficient. So this will involve some of that characteristic. So let's try this. We have these two reactions, and these are the change in enthalpy for those reactions. We need to calculate the change in enthalpy for this reaction. Well, let's sort of pick apart these reactions. We have sulfur and oxygen going to sulfur trioxide. We want sulfur and oxygen going to sulfur dioxide. Well, if you look right here, here's our sulfur dioxide. We know that sulfur and oxygen produce sulfur trioxide. If I reverse this reaction, I can see how sulfur trioxide could produce the sulfur dioxide. So the first thing I'm going to want to note is that I will want to reverse that reaction right there. We're going to want to reverse that. So let's go ahead and write that. Okay, I wrote those reactions down for us. Here's just simply the first reaction. I just rewrote. The second reaction I wrote in reverse. I took 2 sulfur trioxides going to 2 sulfur dioxides and oxygen. That's what I wrote there. So I had to reverse the change in enthalpy for it. I say the change in enthalpy is a negative of this value of negative 198.2 kilojoules, which means it's just a positive 198.2 kilojoules of energy. Now, we still have some discrepancies. Look at this. When I add these reactions together, my sulfur trioxides will not cancel out. And that's a problem, isn't it? How are we going to solve that problem? We can do one of two things. We could either multiply all of this, and its enthalpy, change in enthalpy, by 2. If I multiply this by 2, then I get 2 sulfur trioxides, and those will cancel out. Or I can multiply all of this by 1/2. Either one is fine. If I multiply this by 2, you'll see that in the end, maybe I'll go ahead and do that. It's a little bit more complicated because in the end I'm not going to get exactly this equation, because if I multiply all of that by 2, I will also have 2 sulfurs. So I will end up needing to do another step to reduce this in the end. So it may be easier to multiply this by 1/2, so that way I maintain my single sulfur and I get simply a single sulfur dioxide molecule, and that matches my final equation that we're looking for. So I'll go ahead and multiply this by 1/2. When I do that, I get this equation. So I just rewrote that for us. This is the equation I get when I multiply all those by 1/2, and I also have to multiply my change in enthalpy by 1/2. So I went ahead and made this just a plain positive number, 198.2 kilojoules, multiply it by 1/2. Now I can add all of these equations together, both of these equations. The chemical reactions and the enthalpies I can add together. So when I do that, I can see that my sulfur trioxide cancels on each side. I can see that my oxygen, over on the right side I will have a half of an oxygen, and I have 3/2 of an oxygen here, which means I can, in essence, reduce this to 1 oxygen. 3/2 oxygen minus 1/2 oxygen is 2/2 oxygen. Remember your fractions, which is just 1. So I'm going to go ahead and add these two equations together. Sulfur plus just 1 oxygen molecule produces, on the right hand side, I just have sulfur dioxide. My enthalpies, I can add together this and this. It gives me 296 kilojoules. So I can only use 3 sig figs in this. So that is how I combine those. That is the math involved. And if you go to the next page, I will give you a practice problem to try. Okay, here's your problem to try. You have this equation and this equation with the enthalpy, change in enthalpy for each of those reactions. Calculate the change in enthalpy for the following reaction, this one. So go ahead and write those reactions down and use Hess's law to calculate the change in enthalpy for this reaction. Okay, we have an answer. Negative 310 kilojoules. If you were not able to do that on your own, if it was really confusing, please bring it into class. We'll work on that together. There isn't a separate worksheet for that, so we'll just work through that together. And if you really are thinking this is fun and you'd like to do some advanced proficiency, try this problem. It's a little bit different. Any other ideas you have for advanced proficiency, something that you can come up with to look at more content or go into this more in depth, please just start looking and learning on your own and come and tell me in class. And we'll see you later.